You know, when we think about building a massive skyscraper, there's always this, I guess, this assumption that the primary challenge is just stacking the steel and pouring the concrete. Like you build the structure, and it just stands there solid and unchanging.
Right, yeah. We definitely tend to view architecture as this static, immovable thing once the blueprints are actually executed.
But if you talk to structural engineers, they'll tell you the steel is, well, it's actually the easy part. The real nightmare is planning for all the invisible dynamic forces, like the sudden localized wind shear, or, microscopic shifts in the tectonic plates.
Oh, absolutely. And crucially, it's the chaotic human element, too. I mean, it's the thousands of tenants who all decide to hit the elevator call button at exactly 8:55 a.m., causing this massive simultaneous strain on the system's underlying infrastructure.
Exactly. And that invisible, unpredictable stress test is precisely what we are dealing with today, just, translated into the digital realm.
Yeah.
So, welcome to the deep dive. Today, our mission is to act as your ultimate study partners to help you crack the code of the HPE0-J82 exam.
Which is quite the undertaking.
It is. It really is. And we know the fundamental logistics of it. It's a proctored 90-minute gauntlet of 60 questions. It's delivered in English, and it requires a 63% to pass.
Right. But look, we aren't just going to read you a syllabus or like a list of multiple choice answers to memorize. To truly master the HPE0-J82 exam, you have to understand the architectural trade-offs.
Makes sense.
The goal here is to really deconstruct the actual infrastructure nightmares you'll face, from latency bottlenecks to disaster recovery constraints, and understand the underlying physics and logic of how these storage systems actually handle stress.
Yeah, so no hollow transitions, no textbook reading. We are going to meticulously break down 10 actual practice scenarios. I'll lay out the scenario and all the options, and together we're going to figure out the mechanical why behind the correct architecture.
Sounds perfect.
Let's just kick things off with the absolute foundation, right? The physical storage media and how it handles extreme data demands. So here's our first scenario. Question 1.
Go for it.
Okay, it says, during a storage assessment, you discover that the customer's primary application requires extremely high random read performance. The capacity growth is minimal. Which drive configuration strategy is most appropriate?
Yeah.
And the options are, option A, deploying high-capacity nearline drives to maximize storage density. Option B, implementing a hybrid array heavily weighted towards spinning disks. Option C, using the fewest possible high-capacity solid-state drives to save power. Or option D, selecting a higher quantity of lower-capacity solid-state drives to maximize parallel access.
Well, the correct strategy here is definitely D, selecting a higher quantity of lower capacity solid-state drives. And to understand why, we really have to isolate the specific constraints of the prompt.
Which are the random reads, right?
Exactly. The customer needs extremely high random read performance. That just immediately disqualifies A and B. I mean, nearline and spinning disks introduce rotational latency and physical seek times, which are just absolute poison for random read workloads.
Right, because they just can't physically move the read and write heads fast enough for those scattered data blocks. They're literally spinning plates.
Exactly. They are mechanical. So the real architectural debate here is between C and D, using fewer high-capacity SSDs versus a higher quantity of smaller SSDs.
And if capacity growth is minimal, but we need pure performance, we want more physical drives, right?
Yes. Because more individual drives mean more SAS or NVMe lanes, more controllers, and vastly more parallel I/O queues. It is fundamentally an exercise in queuing theory.
Oh, queuing theory? Okay.
Yeah. So option C limits your throughput because you are funneling all those random read requests through a very small number of drive interfaces. Option D expands the horizontal plane. You're distributing the workload, reducing queue depth on any single drive, and maximizing your total input-output operations.
I think of it kind of like a grocery store. If you design your store based on option C, you have one giant, incredibly fast cashier. Sure, they're highly efficient, but there's still only one checkout line.
That's a great way to put it.
Yeah, and option D is like opening up 20 standard checkout lanes simultaneously. Even if the individual lanes are handling smaller carts, you are processing vastly more customers in parallel, effectively eliminating the queue.
Yeah, that grocery store analogy is a perfect way to visualize parallel workloads at the hardware level. But building a wide parallel storage architecture is, well, it's really only half the battle.
Right.
The hardest variable to architect for isn't the silicon, it's the human behavior interacting with it.
Which brings us to a classic infrastructure nightmare. Let's look at question 2.
Let's do it.
Which characteristic is typically the most challenging aspect to plan for when sizing a storage solution for a large-scale virtual desktop infrastructure deployment?
Okay, what are the options?
Option A is managing the intense burst of simultaneous read and write activity during morning logins. Option B, storing massive individual continuous media streaming files. Option C, handling the steady, predictable, sequential write patterns of long-term archiving. And D, providing continuous access to a single large relational database table.
Right, so the answer is A, managing the intense burst of simultaneous read and write activity during morning logins. In a virtual desktop infrastructure, or VDI, we call this a boot storm or a login storm.
Or boot storm. Sounds intense.
It is. Let's look at why the others are easier to manage. Continuous media streaming, long-term archiving, and a single relational database, so options B, C, and D, they generally exhibit sequential or highly steady-state I/O patterns.
Meaning they're consistent.
Right. The storage controllers can easily cache, tier, and predict those patterns because they aren't wildly fluctuating.
But let me push back on that for a second. Let me push back on the idea of a boot storm being inherently unpredictable. If it's a morning login rush, we know it's going to happen at, say, 8:55 a.m. every single day. The clock itself is highly predictable, so why is it so notoriously difficult to size for?
Well, that's a great distinction. The clock is predictable, sure, but the architectural strain isn't about the time of day. It's about the microscopic alignment of the I/O.
What do you mean by microscopic alignment?
So when 5,000 users click login within the exact same 10-second window, you aren't just moving large contiguous files. The hypervisor is suddenly hit with millions of tiny, highly random metadata reads and writes.
Oh, wow.
Yeah, you're loading operating systems, executing group policies, processing user profiles, initializing antivirus scans, all at the exact same millisecond.
So it creates this massive I/O blender effect. The storage array is slammed with queue depths that just spike vertically in a matter of seconds.
Exactly. And that overwhelms standard caching tiers if you haven't explicitly over-provisioned the flash architecture for that specific microscopic window. You are architecting for a 10-minute window of sheer chaos that requires extreme, immediate read and write speed.
Okay, let's unpack this. We've solved for the chaotic, random bursts of thousands of users. But what happens on the back end? Like when those users are actively querying the core transactional databases, the priority shifts, right?
Yes, it shifts from handling random user bursts to minimizing the absolute write latency of the core system.
Okay, let's look at that specific trade-off. Question 6. In a high-performance database environment where write latency must be minimized and capacity efficiency is a secondary concern, which data protection layout provides the best performance profile?
Okay, the options.
Option A, network RAID 10 or equivalent mirrored striping. Option B, distributed parity with a wide stripe layout. Option C, triple parity protection utilizing low-cost media. Or option D, single parity configured on the highest capacity drives available.
The correct layout here is A, network RAID 10 or equivalent mirrored striping. The prompt explicitly states that write latency must be minimized and capacity efficiency is secondary.
Which is a huge clue.
A massive clue. That tells us immediately to avoid options B, C, and D because they all rely on parity protection schemes.
Right, and in a Tier 0 database environment, parity is a massive bottleneck, isn't it?
It absolutely is.
Because every single time a database writes a block of data with distributed or triple parity, the storage controller's CPU has to execute XOR mathematical operations. It has to calculate the parity bits before it can actually commit the write to the physical disk.
Precisely. And I mean, it sounds instantaneous to us, but when a database is pushing hundreds of thousands of transactions per second, those microscopic CPU compute cycles compound. They compound into tangible, noticeable write latency.
And RAID 10 avoids that.
Yeah, RAID 10 avoids parity entirely. It just takes the data and creates a direct mirrored copy across stripped drives. Because there is zero mathematical overhead required before writing, you get pure raw performance.
But you just take a massive hit on raw storage capacity.
Right.
Because you're literally keeping duplicate copies of everything.
Right, exactly 50% overhead.
It's a stark reminder that what we often consider efficiency, like, saving rack space and drive count with parity, is actually the enemy of pure performance when we were talking about CPU latency. You always have to trade something.
You really do. And speaking of trades, let's look at the ultimate trade-off. What happens when that high-performance database entirely fails and the clock starts ticking?
Oh, the nightmare scenario.
Okay.
Question 7 shifts us into disaster recovery metrics. A customer is designing a disaster recovery plan and needs to ensure that in the event of a primary site failure, the secondary site can be brought online within 15 minutes. Which metric does this requirement define?
Then the choices.
Option A, recovery point objective. Option B, mean time between failures. Option C, recovery time objective. Or option D, service level agreement penalty.
We are looking at C here, recovery time objective, or RTO. This metric specifically dictates the maximum acceptable time frame to restore application services after a failure.
Okay, so why not the others?
Well, option A, recovery point objective, that measures acceptable data loss, like how far back in time your last clean snapshot was. Option B, mean time between failures, is just a hardware reliability metric for physical components. And D is literally just a business contract term.
Right, the SLA penalty.
Yeah, so the specific 15 minutes to bring the site online is definitively an RTO constraint.
I always like to use a simple stopwatch trick for this. Think of the RTO as the stopwatch that starts ticking the absolute second the primary site dies. It measures how long the business can hold its breath before the lack of services causes, well, irreparable damage.
That's a really good way to remember it.
And importantly for you listening, a 15-minute RTO means your failover orchestration has to be highly automated. I mean, you cannot manually spin up virtual machines and reconfigure DNS networks in 15 minutes.
No, absolutely not. That's a critical operational insight. But, measuring a 15-minute RTO gap is one thing. There are specific industries, like global finance, for example, where even a 15-minute outage, or really any data loss whatsoever, is catastrophic.
Oh, for sure. Millions of dollars a minute.
Exactly. So how do you design a network that mathematically cannot lose a single transaction?
Let's look at question 3 to find out. A financial institution requires zero data loss and continuous availability across 2 data centers located 50 miles apart.
Right.
Which data replication strategy should the architect recommend?
Okay.
Option A, asynchronous replication over a low bandwidth wide area network. Option B, schedule daily snapshot shipments to cold storage. Option C, synchronous replication with active clustering. Or option D, periodic tape backups transported via secure courier.
Well, the only architecture here that actually guarantees zero data loss is C, synchronous replication with active cluster.
Because the others just have too much of a delay?
Right. If we look at asynchronous replication, daily snapshots, or tape backups, they all introduce a time delay, an RPO gap, like we talked about. If the primary array crashes at 2 p.m. and the last snapshot shipped at 1 p.m., an entire hour of financial transactions is simply gone forever.
Poof. Just gone.
Gone.
Right. Because with synchronous replication, the primary storage array will not tell the database that a write was successful until it receives a network acknowledgement that the data was simultaneously saved at the secondary site.
Exactly. Both sites have to commit the write before the application moves on.
But let's look at the specific phrasing of the prompt here. It says located 50 miles apart. Why that exact distance?
Yeah.
Like if we're waiting for data to write in 2 places at once, we are literally bottlenecked by the speed of light through the fiber optic cables, aren't we?
We are bumping right up against the laws of physics here. Synchronous replication requires constant back and forth communication.
Right.
If those data centers were, say, 500 miles apart, the round-trip propagation delay on every single write operation would cause the primary financial application to freeze, just waiting for acknowledgments.
Oh, wow. So 50 miles is the sweet spot.
Yes. 50 miles ensures the round-trip latency stays safely within the typical 2 to 5 millisecond threshold that's required to maintain application performance while still guaranteeing zero data loss.
That is incredible. Now, if we're going to rely on a 50-mile real-time fiber optic tether between 2 sites, the network pathway itself has to be absolutely bulletproof. I mean, we can't let a single faulty cable or misconfigured server take down the entire replication link.
Definitely not.
And that brings us to question 5 regarding SAN design. When designing a highly resilient fiber channel storage area network, which topology best isolates faults and ensures that a disruption in one zone does not affect other connected hosts?
Okay, let's hear the topologies.
Option A single large flat network with all devices in a common zone. Option B, a dual fabric design, implementing strict single initiator zoning. Option C, a cascaded loop architecture prioritizing older legacy servers. Or option D, a direct attached storage model bypassing switches entirely.
The topology that guarantees isolation is B, a dual fabric design implementing strict single initiator zoning.
Okay, let's break down why the others introduce massive risk. Why not option A?
Well, option A, a single large flat network, is basically a disaster waiting to happen. In a flat fiber channel environment, a simple state change, like just a server rebooting, sends a notification across the entire network. A broadcast storm could easily take down every connected device.
Yikes. And option C, cascaded loops, creates noisy shared bandwidth bottlenecks that are highly susceptible to disruption.
Right.
Option D isn't even a network, right? It's just direct attached storage.
Exactly. So dual fabric means you have two entirely separate, physically isolated networks. If a switch physically fails on fabric A, fabric B just seamlessly handles the I/O.
Boy, is it.
Furthermore, the single initiator zoning part of the answer ensures that each host bus adapter on a server is placed into its own secure communication lane with the storage array.
Meaning they can't talk to each other?
Right. If one server goes rogue and starts blasting bad traffic, it is logically contained to its own zone. It cannot disrupt the storage access of any other server in the data center.
Okay, so dual fabric isolates the failure domain perfectly. We now have a highly resilient, low latency, actively replicated, fault-tolerant foundation.
We do.
But what happens when the business relying on this pristine architecture suddenly acquires a competitor and needs to double its storage capacity overnight?
That is the big question.
Let's look at modern scale.
Yeah.
Question 8. What represents a core architectural strength of HPE's modern modular storage platforms when addressing unexpected business growth?
And the options are?
Option A, the requirement to perform complex forklift upgrades to add capacity. Option B, the reliance on manual load balancing across distinct storage silos. Option C, the mandatory use of proprietary host networking interfaces. Or option D, the ability to seamlessly scale out performance and capacity non-disruptively.
It is absolutely D, the ability to seamlessly scale out performance and capacity non-disruptively. Options A, B, and C basically represent the legacy administrative nightmares we're actively trying to engineer our way out of.
Yeah.
A forklift upgrade, as noted in option A, historically meant you literally had to buy a larger array, schedule massive weekend downtime, and migrate all your data over just to grow.
It's the difference between having to tear down your entire house just to pour a wider foundation for a larger one versus simply snapping a new fully functional room onto the side of your existing house without ever turning off the TV in the living room.
That is a brilliant analogy. Modern scale-out architectures allow you to dynamically add compute nodes and storage capacity, and the system automatically redistributes the volumes without the host applications ever dropping a single packet.
Amazing.
That automated redistribution is key. It eliminates the manual load balancing silos mentioned in option B. But if we connect this to the bigger picture, when you start scaling out multiple arrays across different data centers globally, managing them locally through traditional methods becomes an impossible operational burden.
Right, you can't be everywhere at once.
Exactly. The control plane itself has to evolve.
Which perfectly sets up question 4.
Yeah.
When positioning an HPE Alletra solution for a customer prioritizing a cloud-native operational experience on-premises, which architectural characteristic fundamentally differentiates it from traditional storage arrays? Option A, its reliance on proprietary fiber channel switches for management. Option B, the requirement to manually provision storage volumes via a local serial connection. Option C, its exclusive support for spinning disk media to lower overall costs. Or option D, the use of a centralized cloud-based control plane for fleet management.
The fundamental differentiator here is D, the use of a centralized cloud-based control plane for fleet management. Traditional management, as seen in options A and B, physically tethers the administrator to the hardware.
Like you literally have to be in the room.
Pretty much. You are
Yeah.
VPNing into local management servers or literally plugging serial cables into the back of the racks.
So when we talk about a cloud-native operational experience on premises, what we really mean is decoupling the management interface from the physical hardware entirely.
Exact.
You can securely log into a unified web portal from anywhere in the world and provision volumes, monitor latency, and execute upgrades across dozens of distributed storage arrays as if they were just a single logical system.
That's the dream. And having that global cloud-based visibility brings us to a major paradigm shift. When your control plane is managing thousands of arrays worldwide, you are suddenly collecting a massive, continuous stream of telemetry data.
Right.
So what is the ultimate architectural use case for all that data?
Predicting the future. Let's look at question 9. A storage administrator wants to transition from reactive troubleshooting to predictive maintenance. Which HPE technology leverages artificial intelligence and global telemetry to anticipate and resolve infrastructure issues before they impact the business?
B options.
Option A, HPE InfoSight. Option B, HPE Store Once Recovery Manager. Option C, HPE Smart SAN. Or option D, HPE SANAV.
The correct answer here is A, HPE InfoSight. The other options are highly capable technologies, but they serve entirely different, highly specific functions.
Like what?
Well, Store Once is for deduplicated backups, while Smart SAN and SANAV are specifically for zoning and managing fiber channel fabrics. InfoSight, however, is the cross-stack AI engine. It ingests millions of sensor data points from storage arrays, hypervisors, and servers globally.
So it's looking for complex signatures. Like if InfoSight's machine learning models detect that a specific VMware latency spike combined with a certain firmware version causes an SSD controller to fail in a data center in, say, Tokyo,
Yes.
it automatically generates a predictive signature, right?
Exactly. It will then warn an administrator in London who happens to be running that exact same infrastructure stack, basically applying a fix before their array ever actually experiences the issue.
Here's where it gets really interesting for you listening. It's like having a mechanic who calls you to fix a part on your car before your check engine light even comes on.
It's remarkably powerful. You essentially have an AI overwatch that correlates the stack for you. It automates support tickets and prevents downtime by literally learning from the global installed base. It transitions the IT administrator's daily life from constantly fighting reactive fires to actually architecting solutions.
Wow. But even with global AI telemetry acting as your overwatch, there is still baseline hygiene required to keep the ecosystem supported and functional.
Oh, of course.
The AI can't do absolutely everything. Which brings us to our final scenario, question 10. To ensure maximum availability and supportability of an HPE storage environment, which proactive maintenance activities should be performed regularly according to best practices.
Okay, let's hear the final options.
Option A, formatting all active data volumes to defragment the drives. Option B, reviewing and applying recommended firmware and software updates. Option C, randomly disabling fabric paths to test failover capabilities. Or option D, physically reseating all storage controllers and drives.
Well, the correct proactive activity is definitely B, reviewing and applying recommended firmware and software updates.
Kinda seems obvious, no?
It sounds almost too simple for an advanced architecture exam, honestly, but it is the non-negotiable foundation of stability. Infrastructure today is largely software-defined.
Right.
If we look at the destructive nature of the other options, formatting active volumes literally destroys your production data.
Right.
Randomly disabling fabric paths introduces entirely unnecessary risk to a live production environment.
Yeah, please don't do that.
And physically reseating controllers introduces static discharge and mechanical risk for basically zero architectural benefit.
Right. And skipping updates means you are missing critical security patches, performance optimizations, and bug fixes. But more importantly, running outdated, unsupported firmware means you might actually invalidate your vendor support matrices.
Exactly.
Which renders all that advanced predictive AI we just talked about completely useless because the system is operating out of compliance. It is the essential, unavoidable hygiene of infrastructure management.
It certainly is. There's no getting around it.
Thank you so much for joining us on this deep dive. Keep questioning the material, keep exploring the mechanics behind the tech, and we'll see you next time.
And what stands out to you? Think about that unseen architectural marvel the next time you trigger an entire data center to spin up just by typing in your password at 8:55 a.m.